Alrighty, so this video we're going to do something interesting, I hope, and that is we're going to try to recreate what would be done physically in an experimental lab using Geiger counters with radioactive sources. Obviously, because of being online and restrictions, it's not as easy to be able to do this in person, and so I'm going to try to give you the sense of doing the experiment and being able to have you analyze the data and work with the data, even though it's more in a virtual sense than actually being in the lab to do it. So hopefully you'll get a good amount out of this. What this experiment is the study or trying to come up with a model of how the Geiger counter or how detection of radiation relates to how far away a radioactive source is. So that is to say, let's say we have something radioactive. I'll put it in green. Here's our little radioactive source. And we'll have a detector, our Geiger counter, and let's say the Geiger counter is over here. Here's the tube. Of course, the tube is by a wire and it's connected to the machine somewhere. Well, the question is, does it matter if I'm trying to detect how radioactive an area is because of a nuclear source? Does it depend on where I measure? So for instance, if I have a Geiger counter and I'm measuring the radiation in a room, does the data that I collect, does it depend on how many radioactive sources there are? And that's it? Or does it depend also on where I'm looking? Now this, you may have an intuitive answer to the question, but it's not necessarily clear-cut as to what the proper answer is. If someone says, how radioactive is a room? Honestly, I would say, well, it depends. How many radioactive sources are there, right? The more radioactive sources are in a room, the more things that are radioactive, the higher the radiation in the room. However, if you actually get your Geiger counter and you detect, let's say there's only one radioactive source in this room. Well, if I look with my detector and I look here, where this Geiger counter is, and I measure for 30 seconds, the machine will tell me, okay, I've counted, let's say, 10,000 radioactive counts, so 10,000 hits. However, what happens if, as I'm moving through the room, my detector gets over here? Now remember, I'm going to assume I can't see what is actually radioactive. I'm just moving around in the room, and now I detect over here instead. And I detect for 30 seconds. Will I still get 10,000 hits? Because notice the actual number of things in the room that are radioactive hasn't changed. It's still just one source. That source is still putting out radiation at the same rate. Nothing has changed except for me where I'm measuring. The actual amount of radiation hasn't. But when I measure, I may get 80,000 instead of 10,000. So now the question is, well, I can't necessarily say that the radioactivity of a room merely depends on how many radioactive things are in the room. Of course, that's true. But it must also depend on where it is I'm measuring. If I'm measuring really close to the thing that's radioactive, then it seems much higher of a radioactivity than if I'm measuring kind of on the far side of the room, really far away from the radioactive thing. Even though the amount of radiation in a room is the same, where I'm measuring, there may be less radiation here than over here. And that's what we want to discuss here. Is there a difference? We want to prove that this is true by experiment. Is there a difference in how radioactive a source feels to a detector, or how much radiation I detect? Is there a relationship between that and where I'm detecting? How close am I to the thing that's radioactive? Now, I've already kind of spoiled the answer. I mean, now that you see this picture, it's kind of clear. If you don't see why it's clear, notice this. Notice that before, when I'm first measuring how radioactive the thing is, remember what's happening with the source. The source is sending out electrons in all directions, right? Randomly, just sending them out all over the place. Now, what am I detecting? How does my Geiger counter detect? Well, obviously, the only thing that gets detected is an electron that has escaped from the source and actually hits my Geiger counter tube. So notice, if I extend these lines, these electrons going like this, these are all missing. Only the ones that go here and here actually hit, but all of these other ones don't hit my tube. So my tube over there, trying to measure for radiation, doesn't even detect all of this radiation. All of that doesn't count. It's only this small little cone that actually counts. Everything else misses. However, if instead I move my Geiger counter really close, let's say here, okay, now notice the amount that's actually getting detected is a much bigger cone. So before, it was only this blue cone here that gets detected, so all of this. Now, we have a big old red cone that's this big that gets detected. Much more of the electrons will be detected. Now, the source is sending out the same amount no matter what. It doesn't know what's going on. But my machine, since it's closer, will feel more of the electrons that are being sent out, and thus the machine will think there's more radiation here. That's what's going on. Now, what we want to do is prove that this is true, and can we make a mathematical model that represents this, or at least tells us how does it depend on it. And what I mean by that is this. If you remember from electricity and magnetism, we have the force felt by a charged particle is K Q1 Q2 over R squared. And what this 1 over R squared says is, as I move further and further away from the charge, that's R, 1 over R squared, if R is getting bigger, 1 over R squared is getting smaller and smaller. So my force gets less and less as I go. But that's 1 over R squared. There could be another, like electric field, could be 1 over R. Or you can have like the strong nuclear force. That goes as R to the 4th, let's say, where it actually gets bigger and bigger as you try to get further away. So we want to come up with something like this, where a mathematical function that says the number of counts we detect goes as 1 over R, or 1 over R cubed, or 1 over R squared. We want to try to figure out what that function is. How do we do it? Well, you have the assignment online. You download it, and there's a number of pages there. There's a little kind of a theory section from a lab manual that you could read through, and it gives you a little of information about this. But I went ahead and I filled out some of the data tables. So what this is if you remember what I talked about Geiger counters, in order to use them, you can apply different voltages to the machine to make it different levels of sensitivity. Higher the voltage, the more sensitive it is. And I talked about how there is like the first little level, first voltage, that barely allows you to detect anything. And that's called the threshold voltage. So that is the least sensitive amount you can be and still be able to detect anything. Well, notice this data table here. We have two columns, so here's one column, that's voltage, and here's another column with voltage. Okay. And then the other column, which is count rate. So really this is, it's like one big long paper, but they had to put it in two different halves. Maybe it's easier to see like this. Yeah, we'll do this. So this is one set of data here. And then it's continued over here. So what do? I have my Geiger counter. I place a radioactive source somewhere close to it. And I set the voltage down pretty low. In this case, I started at 460 volts. And I set the timer for 30 seconds, and I push go. What happens? A 30-second timer starts. During these 30 seconds, I'm detecting how much radiation is here. And if you notice, for the 460 volts, after 30 seconds is done, I get 0 as my count rate. So that means in that 30 seconds, my Geiger counter didn't detect anything. Well, I know this is wrong. I know I have a radioactive source, so that just means I'm not sensitive enough. So I stop, I reset, I turn my voltage up to 480, so I go up by 20. I set the timer to 30 seconds, and I do it again. What do I get? 0 again. So, I'm still too sensitive. Turn it up to 500, again, 0. Turn it up to 520, now I get 5 counts. So, for me, 520 is my threshold voltage. It is the smallest voltage I can set my machine to just barely detect anything. The voltages before 520, I didn't get anything. At 520, I start detecting. So 520 is my threshold voltage. And then I just continue on. 30 seconds at a time, I detect how many counts of radiation I get for all of these different voltages. First column goes all the way up to 720, and then I go to the next side of the page, which is 740, 760, all the way up to 1,000 volts. And I just write down in my table how much radiation do I detect for each of these voltages. And if you notice, in general, as I increase the voltage, the number of counts I get increases as well. Again, it makes sense. Increasing the voltage makes it more sensitive. If it's more sensitive, it can detect more. But notice something. Notice that right around, if we look, let's say here, start looking at 740. 740 volts, I detect 210 counts. 760, 215, so that's not a big change. 210, 215 is about the same number. 780, 210 again, So I've gone from 740 all the way up to 780, and I'm basically detecting the same amount of radiation. 800, I go down to 200, so I'll detect a little bit less. But that's okay. Remember, this is random stuff. We don't expect perfect data. This is going to go up and down a little bit. But still, 200, it's about the same as 210. 820, 215 again. 840, 220, now I'm starting to get a little higher. 860, 240, then 270, so all of these down here, they're just increasing. But if you notice, in this region here, between the arrows, everything is about at 210. 210, 215, 200. And so that means for this range of values between 740 and 820, changing the voltage did not change the sensitivity of my equipment. What is this? This is operating voltage, or at least the region from which I can choose the operating voltage. This is what's called a plateau region, because let's say we were to plot this. If I wanted to plot this stuff, this would be, let's say I would do, let's do count rate, so number of counts versus voltage. So I have, let's start 460, and 460, 480, 500, 510, 520, 540, 560, 580, 600, 20, 40, 60, 80, 700, 20, 40, 60, 80, 800, 40, 60, 80, 900, and so on. So those are the voltages, and then the y-axis will be number of counts. At 460, I'm at 0. 480, I'm at 0. 500, I'm at 0. So 0, 0, 0, all of this is 0. So all of this is 0. Then I start to increase, and I just keep increasing until I get to about 740. So it starts to go like this. And then at about 740, it levels off. And then at about 840, it starts to go up again. So let's say this is about 210 volts. Here's 100, and so on. Of course, if I were doing this for real, I would literally be putting dots, in the data points, and then I'd connect the dots. But you basically get a line that looks kind of like this. You're increasing the voltage, increases the number of counts, and then there's this area here where it really doesn't change much, and then it starts to increase again. This is what's called the plateau region, because it's like a plateau, it's a flat part. When you're looking at the data, especially with real data, it's not always easy to tell where the plateau region is, so you plot it on a graph. This is a Cartesian graph. You plot it, you draw out a best fit line, and that'll help you see the region. Once you have it, the reason to do this is you want to set your machine to a voltage that's stable. So I see, okay, anywhere between 740 and 820, let's say I use 780 volts. That's my operating voltage. So now, when I actually do my experiment, I'm going to set my Geiger counter to 780 volts and go from there. So this is the first thing to do. What you're going to have to do is draw out this graph. I give you this data, I give you some graph paper, fill out the graph. You have X and Y coordinates. All you do is you say, okay, 460, I'm at 0, so 0. 480, I'm at 0. 500, I'm at 0. Then 520, I'm at 5. So let's say this is 5, 10, 15, 20, and so on. Then 540, I'm at 15, so that'll be here. 560, I'm at 22, so 22 would be somewhere up here. And you just do the dots, and you keep doing the dots, and then when you're done with the dots, you basically just draw a line through the dots. So that's the first thing you're going to do. Then, now that we have the operating voltage, we now move on to this. This table is the experiment itself. And what this experiment is here we have distance. So what you have, let's say in the experiment, we have our Geiger counter tube over here, and we'll have the radioactive source. And so first we're going to set it 6 centimeters away. And we're going to, of course, we're at the operating voltage. We set a timer for 30 seconds, and we push detect. So 30 seconds goes by, the machine detects how much radiation is there, and what do I get? I get this value, 300. And then, because I'm trying to do this in a random process, I do a second trial. If you just do one trial, there could be something wrong that happened in that particular experiment. So you do it twice just to ensure the data is good. So I reset, leave it at 6 centimeters, go again for another 30 seconds. This time I got 305. So okay, data's fairly close. Now, what do? I take my radioactive source. I now move it back a little bit. So now I'm at 7 centimeters, so a little further away. And I detect again, 30 seconds. This time I get 280, so a little bit less. That makes sense. The further I am away, the fewer I should feel. Do it for 2 trials, then move it back again to 8 centimeters away, and so on. You keep doing this till you're 22 centimeters away. And you write that information in the 2 columns, which is there. Then what you do is, because the room you're in could have some radiation in it that's not due to the radioactive source, you put the radioactive source away and you just detect the radiation in the room. And that's what this is here, this background radiation rate of 15. That says if you did not have a radioactive source, you would always feel about 15 counts. So when I got 300 for that first one, only 285 were due to the radioactive source. The other 15 were because of the room. So in this column here, average count minus background, I would take whatever the average is. So you got to calculate the averages of the first and the second trial. You get a number. So let's say this is 302.5. This last column, you take the 302.5 and you subtract off 15. And that's what you put in that column. So first thing you're going to do for this one is you're going to fill out those 2 columns. The first one, it's easy. Just take the average of the first 2 columns to get that third one. To get the fourth column, you take the average minus the background. All right, once that's done, now what we want to do is fill out the graphs. There's 2 graphs for this. The first is Cartesian graph. So over here, this is what a Cartesian graph looks like. There's 2 of them. You do one for this plot and one for this plot. Okay, so again, what are you going to do? X and Y axes. Let's say the Y-axis is number of counts. The X-axis is distance. You put the data points in, then you draw the best fit line. The other graph is this weird looking graph I have here. This is called log graph. And that's because the X coordinate is logarithmic and the Y coordinate is logarithmic. So logarithmic, logarithmic. Both column and row is logarithmic. How do you fill out a graph paper that looks like this? This is how it works. We're going to do exactly like we do with the Cartesian coordinates. The only difference is how to label the axes. So let's look at the x-axis first. This is going to be 1, 2, 3. Each one of these main lines. 4, 5, 6, 7, 8, 9, 10. Okay, notice they're getting closer and closer together. That's the whole logarithmic thing. Don't worry about it. Each one of these main lines you see, that's going to be another number. All right, then if you notice in this box, those main lines start over again. So you have 10. Now it's not going to be 11. It's going to be 20, 30, 40, 50, 60, and so on. So for this first box, you go 1 to 10. In the second box, it's 10 to 100, going by tens. Okay, so 1, 2, 3, 4, 5, up to 10, then 10, 20, 30, 40, up to 100. And then you do the same for the y-axis. You have 1, 2, 3, 4, blah, 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 up to 10. And you go 10, 20, 30, 40, up to 100. That's in general. Look at our data. Your data for number of counts goes up to 300. So really what I have to do is I have to make 10, 20, 30, 40, 50, up to 100, and then 200, 300, 400, 500, up to 1,000 at the top. Okay? Once you've labeled your axes like this, all you do is take the data. Look at the first one. I would have, let's see, 302.5 minus 15. That's going to be, what is that, 287.5? So for 6, I have 287.5. All right, where's 6? 6 is here. Then I go up to 287.5, which is right somewhere around here. So there's my dot. Next one, 7. That's going to be at about, let's say, 260. So for 7, I'm at 260, which is here. And then blah, 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 let's say 22. What would 22 be? It's about 20 minus 15, which is 5. So here's 22. I go up to about 5, which is under here. So it's down here somewhere. Switch a line to connect all these dots, which is going to look something like this. Now, it looks kind of messy because unfortunately the graph is really small on the screen and my pen ink is kind of big. But when you're doing it, you'll have no problem. It's all a matter of setting up your axes correctly. The first set, 1, 2, 3, 4, up to 10. The next set is 10, 20, 30, up to 100. For the y-axis, you start at 10, 10, 20, 30, 40, up to 100. 100, 200, 300, up to 1,000. Once you've set up the axes, plugging in the data points is just like you do on a normal graph paper. Put the x and y coordinates in, put a dot there. X and y coordinates in, put a dot. Then you connect the dots with a line. The last thing I ask you to do after you've done those graphs, so at this point, you should have 2 graphs for this data, the log-log graph and the Cartesian. And then also filling out this column, or these columns. And then you should have this graph as well for this data. The last thing I ask you to have is to explain the relationship between distance and number of counts. And that's basically what this first step was. What you will find is that you should get a 1 over r squared type relationship. The reason you get a 1 over r squared type relationship is because what is detected is as if what you have is a sphere of radiation coming out, getting bigger and bigger. And so what is felt is how much of this sphere is hitting the Geiger counter. So it's the amount of the surface area that hits the Geiger counter. And the surface area of a sphere is 4 pi r squared. So that's why you should have a 1 over r squared relationship. Anyway, that is the assignment. Download the data from Canvas. You have these 2 data sheets, the columns, data plots, and you'll have 3 graph papers. 2 Cartesian like this, and 1 log-log graph. First thing you do is finish out these data columns. Next, make your plots. 1 plot on Cartesian coordinates comes from this stuff. You just take the data, plot it in. Draw the best fit line. Next plot, another Cartesian coordinates, but what you're plotting is this data here. Distance and count rate. Last plot is the log-log graph, which is the one that's sitting here, where you're plotting the same thing. The final thing is to just write up or type up, or however you want to do it, the explanation for why the distance, there is this distance dependence for radiation. Now, of course, if you have any questions, feel free to email me, let me know. But go ahead and work on this and turn it in before its due date. Until next time.